everyone, thank you for joining me for this video. Today we're going to be learning about the equilibrium constant Kc. And so the first learning objective is to learn the expressions for the equilibrium constant for homogeneous reactions and calculations of the equilibrium constant from provided equilibrium concentrations. And then we're going to estimate the position of equilibrium from the magnitude of Kc. Now, if we have a reaction such as this one, so this is just a general reaction, we know that Kc is equal to the concentration of C at equilibrium by the power of little c, which is the number of moles there are of C, multiplied by the concentration at equilibrium of D, multiplied by the moles of D, and then over the concentration of A at equilibrium by the power of the amount of moles there are of A, and then the concentration of B at equilibrium by the power of the moles of B. And so we can determine where the equilibrium lies, because if Kc is large, then that means that there are a lot more products than reactants, because the top would be bigger than the bottom of the fraction. And so we know that the equilibrium lies to the right. So a large Kc implies that the equilibrium lies to the right, and the opposite is the case as well. So if we have a small Kc, that means that we have quite a large bottom of the fraction, and so we know that there are quite a lot of reactants. So the equilibrium lies to the left. So now we're going to discuss how to work out the Kc of a reaction. The simplest Kc calculation questions actually give you the equilibrium quantities already in the question. So the equilibrium quantities are basically how much of everything there is when it is in equilibrium. So calculate the Kc for the following equilibrium given the results of an analysis of the equilibrium mixture, which show that the concentration of SO2 equals 0.230 moles per decimeter cubed, oxygen is 1.370 moles per decimeter cubed, and SO3 is 0.920 moles per decimeter cubed. So what we do is we simply just plug it into the equation. So we have Kc equals x at equilibrium multiplied by x, and then we have A, which is at equilibrium, the concentration of A, and we multiply it by how many moles of it we have, and then we multiply that by the concentration of B, and times it by how many moles of it we have. So if we call this A, this B, and this X, we should be able to find this. So that means we're finding the concentration of SO3 at equilibrium and then multiplying it by 2, because this is the amount of moles of SO3 we have. And then on the bottom we'll have SO2, the concentration of it at equilibrium, and multiply that by how many moles of it we have, and then multiply that by the concentration of oxygen taken at equilibrium, and the moles of that is just 1, so there's no power. So it's really important to remember that Kc measures the ratio with the products at the top, because if you did this fraction the other way around, it wouldn't work. So using these values that they've given us for the equilibrium mixture concentrations, we can then work out Kc. So we have 0.920 squared over 0.230 squared times by 1.370, and that gives us 11.7. Now, the thing with Kc is that the units of it change depending on the reaction. So the way we work out the units is that we use the formula that we have here, but we cancel out some of the units. So for example, for this example, on the top we have a concentration squared. So we have moles per decimeters cubed squared. And then on the bottom, we have another moles per decimeters cubed squared and just a normal moles per decimeters cubed. And so then we cancel. So I know that I can cancel this with this. And then we're just left with 1 over a mole per decimeters cubed. And so the units for this case C are mole to the -1 and then decimeters cubed, because we have 1 over a mole per decimeters cubed. I've also rounded it to 3 significant figures because in the question everything is has been rounded to 3 significant figures. So that's what gives us a clue as to what to round the answer to. So this question is slightly different because we're actually given the case C, but we're told to work out the equilibrium concentration of one of the reactants. So feel free to pause the video and try it out yourself first, or you can follow along. So in the following equilibrium, Kc equals 54.1 at a particular temperature. The equilibrium mixture was found to contain hydrogen at a concentration of 0.480 times 10 to the minus 3 moles per decimeters cubed, and hydrogen iodide at a concentration of 3.53 times 10 to the minus 3 moles per decimeters cubed. A asks us, what is the equilibrium concentration of iodine? And so we don't actually need to work out the equilibrium moles because they've already told us them. So we have 0.480 times 10 to the minus 3 moles per decimeters cubed of hydrogen and 3.53 times 10 to the minus 3 moles per decimeters cubed of the hydrogen iodide. And so using the Kc equation, we can then work out the equilibrium concentration of I2. So we have that Kc equals the concentration of Hi taken at equilibrium squared divided by the concentration of hydrogen at equilibrium times by the concentration of iodine at equilibrium. And so if we rearrange this formula, then we can find this equilibrium concentration of the iodine. And so the equilibrium concentration of iodine is equal to the concentration of hydrogen iodide squared at equilibrium divided by Kc times by the concentration of hydrogen at equilibrium. And that comes out to be 3.53 times 10 to the minus 3 squared divided by the Kc, which is 54.1, times by 0.480 times 10 to the minus 3. And this comes out to be 4.80 times 10 to the minus 4. And I've also rounded that to 3 significant figures because everything else in the question is. So for B, what effect would doubling the concentration of hydrogen have on the equilibrium position in Kc? So if we have a look at the equation, if we doubled the concentration of hydrogen by Le Chatelier's principle, the equilibrium would move to counteract that change. So try to decrease the concentration of hydrogen. And the way it does that is to produce more products. And so the equilibrium shifts to the right. And the thing to remember about Kc is that it is not affected by concentration. So the Kc remains at 54.1. For C, what effect would increasing the temperature have on the equilibrium and Kc? So when we increase the temperature, the equilibrium acts to decrease the temperature, so it favours an endothermic reaction. So looking at this bit here, it says that the delta H is bigger than 0, which means that the forward reaction is actually endothermic because it's positive. It's got positive enthalpy change. And so that means that when we increase the temperature, the equilibrium will favour the endothermic reaction, which is the forward reaction, and so the equilibrium shifts to the right. And what happens to the Kc is that because the Kc is the ratio of products to reactants with the products on top, that means that if we produce more products, that means that fraction will be a lot bigger. So Kc actually increases. Because Kc is the concentration of products over the concentration of reactants. So if this has increased, the product has increased, that means that this whole fraction will be a lot bigger. So the Kc has increased.